Yeah. Okay, very good. So today we have a very dense program, and we're going to talk about working with structural inputs and outputs. So what does this mean, and what's the agenda for today? So first we will understand what this problem actually means. I mean, what is the structural inputs and outputs, okay? And then we will talk about decoders and encoders, which you have probably heard of, but maybe don't really know what this is all about. The first thing I want to say before we go into any depth here is that what you encoders and decoders really have nothing to do with I encrypt something and I decrypt something. Okay, so these names are really historical. So if you believe that encoders take something that is compressed and later they are uncompressed by a decoder, then this class will be very important because this is not what this is about. Okay, so these names should actually not, these things should have different names somehow, but for historical reasons, it's like this. Okay, so what's this problem of structural input? So suppose that we now want to do the following. We have an input, and the input is a map where we have locations of some cities, for example, okay? And we want to find the cheapest route that visits all of them. Okay, this is the traveling salesman problem. It's one of the most standard problems in computer science. So the traveling salesman problem. And we will maybe assume that the costs to travel between two places depend a bit on the hour on which we travel, because going from Trier to Bogota is not the same 2 a.m. in the morning or 2 p.m. in the afternoon. Okay, and maybe there are also travel restrictions. So, for example, in Europe, there are, or I mean, here as well. I mean, so on some during some hours, maybe you cannot travel between two places because there are travel restrictions, okay? So that would be maybe an input for us. Now, this is not an input that we are used to map because, well, maybe you can describe every location here with a coordinate that would be like 2 columns. Okay, 2 columns, X, Y coordinate for the city. But we also, in addition, have like these information of for each pair of these locations. Is there a direct connection? If so, what's the travel cost? Okay, also there are like other restrictions. So it seems like a bit difficult to use like the standard neural network architectures that we use currently. Also, here we have 20 locations, but what if we have 15 or 35? So what if the number of locations is variable? So then the standard networks, especially the fully connected that we currently have, wouldn't really work. So that would be the input. The input is variable length. It has structural information. For the output, maybe we want a sequence. The sequence tells us in which order do we visit the different places. Okay, that would be so something. Now, that means that my network must output a list size 20 if I have 20 cities. But if I have 15 cities, that it must output a list of 15. So how would that work with a fully connected network? Answer: the way how we do it currently, it wouldn't work because we have a fixed output size in the network. So we don't have this ability of flexible variable length. Yeah. Now, for starters, let's look at a much simpler problem than that. And the simpler problem would be machine translation. Okay, so look at this sentence. He went to the bank to open a savings account. Okay, so we have this sentence in English and we should translate it to Spanish. Now, why is this much simpler? We didn't used to think that this is a simple task. And actually, until ChatGPT came up, machine translation was really not working very well, right? Well, let's say not ChatGPT, but GPT in general, because GPT improved enormously on this task. But I mean, even today, I think Google Translate still hasn't adopted the GPT mechanism. So historically, that seemed to be like a difficult task, and it was a difficult task. Why do I say it's very simple? It's very simple from a syntactical viewpoint, because here, the only thing that we have is once we say that we have a word embedding, then this is only a list of vectors, and we do not have more structure. It's just a list of vectors. Or before the embedding, it's a list of indices. For each word, we have a number, an index, right? And this is just a list of integers. So structurally, this is not very complicated because we don't say that we have complicated connections between items like in the graph, where you say between this and this city, you cannot travel in certain times. That's a much, structurally speaking, a much more complicated situation. So here, this is sort of easy, at least syntactically speaking. Okay? But even in this simple situation, what we need to be able to do is now, if we want to have a machine that can translate sentences, well, we need a machine that can process inputs of variable length, because we don't want a machine that can translate only this sentence, and we also don't want a machine that can translate sentences of size exactly 10 words. But we want a machine that can translate any sentence, okay? So input would be variable length, output would be, well, also variable length. And actually the output length is different from the input length because we will not just translate every word to something, and the output sentence will not have 10 words, maybe by coincidence, yeah, but not in general. So the question is how we can do something like this. So I'm talking here about structural inputs and outputs, and some terms that you've certainly heard of is structured data and unstructured data. I want to disentangle this a bit here so that we understand the difference. So structured versus unstructured data talks about the format across samples. So do I have tabular data or not? That's been the question. Structured data means somehow I have tabular data. Okay. And unstructured data means different instances have different lengths in the description. So maybe I have images of different sizes. Or I have texts of different lengths. Now, because these objects have different sizes here, we call them unstructured, which is maybe not a very good term. So I'm not saying that this is a good thing to do. I'm just explaining to you how are the words used typically. Okay. So structured means table. Unstructured means I cannot have a table because my objects have different lengths or sizes somehow, and this is why it's a bit unstructured. But this is not really what I'm talking about here. Okay. So the other thing is structural versus non-structural data. Structural now doesn't look at, I have two instances. One has a different description size than the other. But I'm looking only at a single instance. And the question is, inside a single instance, do I have somehow structural information? So I have a sentence, and the sentence is just a sequence of words. And there is no explicit additional information. Okay? So if I have just a sentence, then I'm in the unstructured scenario, but also in the non-structural scenario, because there is no real structure. I have a list, but I do not have an explicit information that I don't have an explicit information. That third word refers to the first word, for example. Implicitly, that can be there, but not explicitly. If I have a graph, so I could have one instance is a complete graph. And in the graph, I have two nodes. And I'm saying the node that corresponds to Dylan is a friend. Dylan is a friend of Santiago. Yeah. Then I have explicit information that two sub-objects like atoms in my instance are related to each other. That's an explicit information. Yeah. Or if a molecule, then I have atoms in the molecule, and some of them are connected explicitly. This is an explicit information of connections between objects in my instance. Okay, so this is structural data. I have two cities, and for a pair of two cities, I have an explicit information. What's the travel cost, or what is the travel restriction, or whatsoever. Okay. So I can have actually 4 cases. I can have data that is structured, like tabular, and is also structural, but this is rare or artificial, because structural means, like by definition, this means if I have something structural, it will be difficult to capture it in table. Okay, so I could, in theory, create a table for data that is structural, but it's really not very common. But I can have structured data that is non-structural. That's the standard tabular data. This is my pandas data frame scenario that we do. And if I have unstructured data, then this unstructured data could be structural, means I have flexible sizes. Flexible sizes means unstructured, but I could have structural information inside. Okay, how does city A relate to city B, for example? Graphs, molecules. Or I have unstructured data, flexible sizes, but there's no specific structure that describes a single instance. Okay, so here I would be in the case text, images, for example, so unstructured, non-structured. So it's a bit important to separate like these two concepts. Okay. Yeah.
In this case, if I have a data in JSON format, this is a structured format, and on the structure,
JSON would be unstructured,
yeah,
because it's not table, unless you have like for every, unless you're I mean, you can also write a pandas data frame as JSON.
Mm-hmm.
So if your dictionary is of a very specific shape, then it could be structured. But in general, if you just say for some, like my JSON is a list. I have one entry for every instance. And in every instance, I have a dictionary that can have different fields that are not unified, then this is unstructured. Yeah. But the question is now for each instance inside of that, do I have something like sub-objects that relate to each other? Is there some structural information that describes a single instance? This could be or could not be. That is not a matter of whether your format is JSON or not, but whether how you use that format.
Sorry. Does the string data could be considered structural and unstructured? I think that maybe that's the case.
Which one?
String data, like for example, the value of initial asset, for example.
Yeah. Stream is basically another dimension here, because stream just tells you how does the data arrive. Is it in a batch? Does it come in a batch or in a stream? So it's not relevant for this question here.
Okay, but the fact that this is a string data set or string data source could may be considered form of structure. Because that's
Okay.
Let's say that, for example, I'm getting constant every second I'm getting a new observation of the value of an asset. If I take a single observation, that observation has a systematic relationship with the one that is before and after that, and it's explicit. But also, I could just organize that into a structured data set, meaning that it's like tabular data. That is
no, but wait. So when we talk about structured, structural, and we talk about explicit connections between things, we're not talking about explicit connections between instances. We're saying inside a single instance, the description of a single instance is so complex that I have structural information. So a single instance could be a description of a molecule, a chemical molecule. How do you put this into a table?
It's
difficult.
Impossible.
Yeah, it's almost impossible, but so this is why this here is rare, okay? This is typically unstructured because you say I have a set of atoms, and then you say how the atoms are connected. And all of that is a single instance. So inside of a single instance, you have sub-objects, so to say, which are somehow connected or not. or in some kind of relationship. And to describe these relationships, you need this, like, this is the structural part, okay? So it's not about I have a stream and instance I is connected to instance I plus 1 or I minus 1. Because structural means I've structure inside of a single instance, not between instances. That's not the question. Okay. Yeah.
The definition of a structure and a structure is related with completeness, completude, and dimensionality. I mean, a table is complete because it has all rows and all columns, and it has fixed size.
Fixed amount of columns. This is the important thing, and that would mean structured.
But also the JSON may have.
Yeah, this is what I said. So I mean, you can also represent a table in JSON, but JSON is just more flexible format.
JSON itself is a structure.
That's not the point. The point is not which language do you use. So maybe you use JSON, but actually all of the instances have exactly the same fields. Then you could take your JSON and put it into a pandas data frame. Yeah. But in JSON, you can do more things. And it could be that different instances have different fields somehow, or different sizes. And then you're in the unstructured case. And whether that is now structural or non-structural, that depends on what do you put into the description. If you just have like atomic fields, then this is non-structural data. Yeah. But if you use the JSON to say, okay, I have these and these atoms, and then I have a field that describes the relationship between the atoms, then that would be structural data. Good. Okay. So that's to motivate a bit the scenario and to see, okay, yeah, well, if we now start talking about these things, certainly with the networks that we've seen so far, we can do a lot. So that leads us to the notion of decoders. Let's first assume only the simple case of machine translation, okay? Like I get a sentence and I have to produce a sentence. Now, a decoder is any function g that maps from x to y, where x and y are sets of tensors. This looks a bit strange because, I mean, this is what a neural network always does. I take a tensor and I produce another tensor, maybe a vector. So what's special about this? What is special is that in a standard neural network, well, X is not only a set of tensors, but actually it's a vector space. Okay, so typically you would say maybe you would say that this set X is like maybe R to the 6, because you say I have 6 attributes. And every instance is described by 6 attributes. Or maybe you have an image. Yeah.
Wondering if we can rotate the camera so we can see the whiteboard.
I can connect to the call and use my cell phone, for example.
Yeah.
Yeah, but I don't know whether from that angle you can.
I don't know if it's.
Well, it's pointless. I can see.
TV, but
And maybe we have, I don't know, we have images 30 by 30, then the input space would be something like this, or maybe RGB, then our instances would be a tensor that size, okay? This is what we always did. Now, what's different now? What is different now is that we say we don't fix. There is at least one dimension that we do not fix. So here, maybe we say, okay, I don't know this. Here I have a t, but the t can be different for different instances. Okay, that's the difference. So a decoder must be able to treat instances that do not have a specific known dimensionality, but they, at least in one dimension, they can have a variable length, okay? Now, this is a tremendous change. Doesn't look so big, but this is a tremendous change. Because now such a function, such a decoder must be able basically to do two things. It must be, so if x is not restricted, so if x is not restricted, so both can have variable length items. And why do we need this here? Because if we have a sentence, then the sentence, well, the sentence is, maybe we have an embedding of size 6, then we have t tokens of size 6, one for each word in the sentence, and we don't know what is t before. T depends on the concrete input. And for y, it's the same thing. We need a variable length for the translation, okay? So if x is not restricted to a fixed format, then G must somehow be able to process a variable length input. Right? In at least one dimension, maybe even in more than one dimension. Yeah. And if y is not restricted to a fixed format, then G must be able to generate some kind of sequence. So, yeah. So it must be able to generate. So here are two different requirements. Yeah, if x is variable length, then G must be able to process variable length inputs. And if y is not restricted to a specific dimension, then it must be able to generate variable length. Yeah. So, and a decoder is any function that is able to do that. So here are some examples. First, every fully connected network for tabular data is a decoder. Because every neural network that we know is a decoder, because we are just like making the notion more general. Because every standard vector space also complies with these constraints. Yeah? So it's a strict extension of what we had before. So everything that every standard neural network is also a decoder. Yeah. Then what we saw before, we have this traveling salesman problem, but now let's forget about the constraints. We will just say simple TSP, everything is connected, and what are the travel times between pairs. This can also be done with a decoder, because I can just encode the information about cities in a list, and I can give it to this machine. This is just a tensor of a variable length. I can give it into this network, and he can produce a list of locations. So this could be done with a tensor as well. The core of GPT, I have a list of words. I output other words. This is also what a decoder can do. But we don't always need flexible size in both. So here's an example of, we have a fixed size input. For example, an image, size 100 pixels times 100 pixels, for example. And our function can only handle images of that size, nothing else. Then the input shape is fixed. Right? But then the task is that it should generate a textual description of what it sees in the image. And the output is variable length, because depending on what I see there, my description will be longer or shorter.
I'm sorry, it means that if I'm going to create a decoder, it's going to take a non-fixed amount of images in the input and a non-fixed amount of images in the output. I necessarily have to have some kind of preprocessor, or is not.
And that would be the question. I mean, the big part of the class will be about understanding how can we do this. But yeah, somehow you will need the ability to process this variable. Well, here it's fixed size input. But the question is, I have a fixed size input image. How do I produce a textual description from this with a standard neural network? We really have no idea how this could be done currently. Okay? It could be also the other way around. I give you a variable length input, and you must produce a fixed size output. For example, I give you an electrocardiogram of variable length. You must be able to process it, but in the end, I just want to have one information. healthy or not? Okay, so I translate a variable length input into a fixed size output. So all of these are decoders, and a natural question should be, and I already said it in the beginning, I mean, where is the decoding here? We're just translating, we're taking inputs, producing outputs. Where is the decoding? And the answer is there is no decoding. So the name doesn't make sense, okay? But we need to know that this is called the decoder. And next week, we will also understand why it is called a decoder for historical reasons. But I really want you to associate the word decoder only with anything that can map inputs to outputs, where inputs and outputs may have variable lengths. That's everything. There is no thing like I decode something. Okay.
Maybe the word code, this case in the general sense, is because once you give an input, you expect always the same output regarding that. Yeah. I mean,
But not even that would be the case. So for the same input, we can even generate, and actually we will generate different outputs for the same input. It's also not like,
I know, but maybe for historical reasons, they
No,
think in that way.
I know why this is like this, and I can also explain you next week why it came to have this name. It's like today, nobody would call it like this, but it's for historical reasons. I explain next week. It is very clear why they have this name, but only that today it doesn't make sense anymore. But still, they have the name, and the name will not change. Okay. So there is a good reason why they came to have this name, but this reason went away. It's not there anymore somehow, and but the name stayed. Okay. Now let's consider again this case of translating the sequence. And the question is now, how would we do this? Let's talk about how we implement this. How would we do this? How would we process variable length input tensors, and how would we generate output tensors with variable length for different that is different from the output? So let's say our input sentence has length 10. So how do we manage this? And then do we generate a sentence that maybe has length 8? Yeah, that is even different. So we have currently only seen two architectures. I mean, in this course, we have seen none of those. So deep learning with me, we have seen only two architectures, the fully connected network and the convolutional networks. Okay, so a question is now, sorry, I will take out this slide. So the question is, how can we, if we only look at these two architectures, how can we use these to solve this task? Yeah. So here's how it goes. We will look at three different cases. First, we will see if we have variable length input. What do we have to do? Then what is if we have variable length output, but fixed input? And then variable length output and variable length input together, okay? Then we have all four, okay. Well, the first case where both prices are fixed, input and output, we have this covered already. So now we cover the three cases where at least one of them is variable length, input, output, or both of them. Yeah. So if the inputs are variable lengths, well, for a convolutional network, actually this is not a problem, because the convolution by definition will just take the input and scan over the whole input, and it doesn't matter how big it is. Only at some point when we want to produce a prediction, we can come into problem as soon as we leave the convolutional world. Because if you remember correctly, at the end of a convolutional network, one typically puts a dense layer, fully connected layer, okay? And that is also for some reason, but in principle, like the input, if I have convolutions, I can treat variable length input sizes without a problem, okay?
But if I have an instance, I mean, with images, in a CNN, I need to define the size of the instance.
No, you don't need to do that.
Yeah, I can go over the entire image, but I need to define if the spot that I am trying to.
So you don't have to say my images will be size 32 by 32. You don't need to do this. In convolutional networks, the only reason why you have to do it is in standard scenarios is at the end you need something of fixed size. And if you have the convolutions and you don't know the initial size, then at the end you don't know how many neurons you will have. Okay, but there are ways around that. Actually, I will show a way around this. So the convolutions themselves, they are completely agnostic to the input size. The problem is not in the convolutional part, but in the fully connected part. So the convolutions, you can apply them to any shape. They will work. What does not work is at the end, if you want to use them in a fully connected layer. Because there you have a fixed number of neurons, and this number of neurons must match the output of the convolutional blocks. Yeah. So yes, if I'm in the very standard situation, I don't do anything, then I can have problems if I don't specify the size. But this is not because of the convolution, but because I say in the end, I have a fully connected layer with 65 neurons. But this 65 only works for images with a specific size. But in principle, then the convolutions can handle variable length. What can we do for a fully connected network? Well, there is a very simple trick. The fully connected network has a fixed number of neurons, and that is completely incompatible with variable length. But we could just say, well, we define some threshold, which is called here Nmax. Nmax is like the maximum input size that we will be able to handle. Okay, and then we just say, let's use this number as the number of input neurons in my fully connected network. Now, what happens if I have an instance like this? Let's say I can treat sentences up to a size of 20 words. Then I have 20 input neurons, or 20 times the embedding size, maybe. Yeah. Okay, now I have a shorter sentence. What do I do? Which information do I put into the last neurons where I don't have a word? Well, I will just invent me a new word, which is called pad or padding. It's like a word that doesn't really exist. It just says, here's nothing, like the word without a meaning. And I will just fill up my sentence of 10 words with 10 empty words. And then I have a sentence of 20 words, and I can put it into my network. Okay. So it's like filling up the sentence with empty words, not random words, with an empty word, a specific word that says here is nothing. No? What if my sentence is longer than 20, maybe 30, but then I can cut off the last 10 words, and I only have a sentence of 20. Okay? Is that a very good solution? No, but syntactically it will work. Okay. So then if I use this technique, I can guarantee that the input for my network will be of a fixed size. And if I have that, I can use a fully connected network. Agreed? So this is a kind of pre-processing, where I fill up or where I cut. So I make sure that my sentence that goes into the network has exactly size 20. And actually, this is still, in a sense, what happens even in modern architectures like transformers. Not exactly in this manner, but the idea, the principal idea of like this padding will stay important also in when we look at more modern architectures. Okay. So first check mark, we can now handle variable length inputs. And how do we do it? Well, we don't really do it. We just make them fixed size. Okay. And the idea will be to choose Nmax large enough so we are never ending up in this case. So let's make nmax big enough, like 100, because we don't have sentences that are longer than 100 words. So that we only have to use the first case, pad, put in the empty word. So this doesn't look too bad, even from a theoretical viewpoint. Yeah, because in the end, we're just saying, I take your variable length input. It must be shorter than 100, and I fill it up with like placeholders. And then I can do something with this. And you will see at home that you can do, you can already work with this, okay? So we will, for example, use it to, at home, we will use it to sort lists of numbers. You get an arbitrary size list of numbers, and your task is to order this. And you will use exactly this technique to fill up the sequence with like add symbols, and then you can and you will have a fixed size representation, and you use a standard neural network for this part. No convolution or other crazy techniques needed. So first check mark. Second case. Now, how can we make sure that we have a fixed length output? Well, this is easy in the fully connected network, because our fully connected network just has a constant number of neurons in the end. So there we don't have a problem. But what happens in the CNN? The convolutional network does not happen. Because in the convolutional network, if I have a variable length input, then also at the end of the convolution, I have a variable length output. Because if I have a time series of length that 100 and my window is of size 5, then I will have a time series output of size 96. So depending on the input size, the convolution will also output something of variable length. Yeah? And to fix this, you can use something that is called global pooling. Global pooling just takes the whole output sequence, like we see this 96 length output sequence of the convolution, and we just take the maximum value of these 96 values, or the average, or the minimum, or whatever. We aggregate this variable length sequence into one number. Well, and if we did this, well, it didn't matter how many numbers we had. Yeah, we can control, we are only left with one single number. Now, typically, you don't want to reduce the whole sequence to just a single number, but you want like, well, from this sequence of 96 pieces of information, I somehow want to infer 20 features and not just one feature. Well, how can you do this? Well, you can apply a 1D convolution over this map with several filters. This basically creates a copy of this 96 features, this 96 length time series. Okay, so I have a single copy of this, and then this 1D convolution of size 1 will create several copies of this, and then for each copy I can derive a different feature. From the first copy, I take the minimum. From the second, the average. From the third, the median. From the fourth, the variance. From the fifth, the maximum, or whatsoever. Okay. So this is global pooling. Global pooling means, we saw pooling already in the deep learning course, right? But we only looked at max pooling, and pooling is also like a window technique. Here we're saying we're using a pooling layer that doesn't go in a window, but we just take the whole object and compute a single number. Okay, and this global pooling is really a very important technique, and it has been used in GoogleNet for image classification exactly in this way. And if I do this, I get rid of the restriction that my convolutional network has to have a fixed input size. I can use images of any arbitrary size. There's no restriction anymore, and I still get a fixed output.
Size and layers.
Size and
Layers, because you can, for example, with satellite images.
yeah. Also.
2 inputs, 1.
Yeah. But this is the channels that you have. This is independent, and because the channels anyway disappear after the first convolutional layer. So this is no problem. So if you use this technique, you can handle images of arbitrary dimensionality. Yeah? And you still can always guarantee, no matter what's the input size of the concrete image, you can always guarantee that at the end of the network, you have a constant number of neurons, which is what you want for classification.
My question is because maybe we are thinking in the convolution by channel, but maybe I want to do some convolutions across the channels.
Yeah, that would be just a 3D convolution. This is just a question.
5 or 6 or 11, and in some cases with an input of 11 channels, but in some cases with an input of
No, sorry. But there's a misunderstanding. So if you want to convolve across the channels, which is not typically done, by the way, but if you want to do it, then you need only a 3D convolution, no matter how many channels you have. So I've not known ever a case where you need more than a convolution in more than 3 dimensions. I don't believe that use cases exist.
Yeah, with satellite images, I want to identify some relations across all layers, all or channels.
Yeah, that's no problem, but
In that case, why I need to restrict the convolution to 3D? If I want to.
no, that's not the point. But that's a really different topic. We can discuss this off topic. It's not the dimensionality of your convolution does not depend on the number of channels you have. And actually, even for RGB images, which already have several channels, you would not use a 3D, but just a 2D convolution. But maybe we can take this apart and discuss this offline. Okay, and then the question is, how can we create variable length outputs? That's the third case, third of 3 cases. How can we produce variable length outputs? Well, in a convolutional network, again, this is something natural to do because my convolutions produce, by definition, variable length outputs. This could be nice, but the question is whether it's what I want, because the output shape is somehow dictated by the input shape and the kernel size. Okay, so it's not like I'm completely flexible in the output with respect to the length. And somehow what's going to happen here is pre-programmed. So syntactically, convolutional networks can produce variable length outputs. Actually, that's what they do. But it's probably not exactly what we want here. In principle, we could use a convolutional network to translate language. Why not? We could certainly do it, and maybe it's also a good idea to make an exercise at some point of time. But how do we do this now for a fully connected network? So how can we use a fully connected network to produce a variable length output? Well, there are 2 ways how we can do it. The first is very simple, and we just apply the same trick as we did for the input. We say, okay, also for the output, we assume that there is some upper bound. We will not produce sequences that are longer than 100. And if we know this, then we can just create so many neurons in the output layer that we would need at most in this case. So for example, if I want to produce sentences of length up to 100, and I encode the word that I want to predict just with an index, then I need just 100 neurons. Or I could have logic for the different words, then I would have a matrix. But in the end, the number of neurons in the last layer would be fixed.
But to understand, yeah, up to wherever the number, but the user, the model, in some cases needs to deliver just partial.
Yeah, exactly. But this is a technical question. So first, your network can produce. So you again have this symbol, the pad symbol, and you say, I'm producing now a sentence of 15 words, and then I only put pad. Okay. And then you have a post processor that will just take away everything that is pad, and then you have a sentence of 15 words, right? Okay, so this would be here, for example, if I have k minus 1 classes. So for example, the classes are my words. Well, then for every word, I need to provide maybe a logit and one additional for this case, for the pad word, because my network also has to be able to say, and here I don't put anything. So this is an additional artificial class, so to say, that he can produce. And then for every possible position in my output sequence, I need to specify the probability for each word. So I have k probabilities for each position that gives me this number of neurons. If I have a regression task, I don't need this here, then I just put a number into each. So if I just want to predict this, like how does my stock portfolio evolve, then I would just put a single number for each point of time. And I do a forecast for 100 steps, and my Mmax would be 100. Okay, so I predict 100 numbers. And then I can use a fully connected network to do this. And this is exactly what we do in the homework exercise. So the standard neural network can be used to treat variable lengths inputs and variable length outputs, and also both together. We only need some like pre-processing to fill up the missing parts that we don't have with pads in the inputs, and we need a post-processing where we remove the pads again from the prediction. And if we have this, then we can use fully connected networks also to work on sequence. Only inconvenience, we somehow have to define this Mmax and Nmax, but well, often we can find reasonable values for this if they are large enough. Okay. Now, there's a second way to do this, which is interesting and important. So what in this solution here, what my fully connected network does is it takes the inputs, processes them somehow, and then it predicts all the output sequence simultaneously. Because I have this number of output neurons, and the value for all these neurons is just like predicted at once, right? But I could also think, well, if I have a task to generate a sequence, why do I not generate a sequence? Like sequentially, iteratively, one by one, okay? And importantly, if I do this, for the prediction of the ith word, I could already use what I predicted for the I minus 1th word. So that looks like an interesting additional approach. And I can also do that with a fully connected network. So in an iterative approach, we would say, we now do a loop, okay? And in each iteration of the loop, like in iteration k+1, what we input now into the fully connected network is the tensor, well, the original input sequence that we had, like the English sentence, but also everything that we ourselves have predicted before. Okay? So in the first round, iteration 1, k is equal to 0, and then we don't have any y here because we don't have predicted anything yet. But in the second round, iteration 2, k is equal to 1. And then we also we input into the network not only the original sentence that we should translate, but also what was the first word that we generated. Yeah. And this symbol here is just a concatenation. It's like put them together into a list. Okay, and when do we stop this? Well, we can stop this at latest when we have Nmax symbols, because we have a predefined maximum length of this sequence. So we can stop our loop once we have reached the maximum size, or we can have a special symbol like this path symbol, and we say, as soon as the network produces the path symbol, we know that it wants now to finish the sequence, and then we stop this process and just fill up with paths from there on. Okay. Good.
The thing is, how do you stop that with meaning? I mean, in phrases, you can put some limit in tokens, words, whatever, but maybe that ends with some preposition and you need additional meaning to come.
Yeah. So I mean, the M max should be large enough. So you say the sentence will not be longer than that. No reasonable sentence is longer than that. So that's one thing. And other than that, you don't take a decision. It's the responsibility of the network to learn when it should stop. And how does it stop? It produces the path symbol. So it should learn when to produce that. And that looks like a difficult task. And it is a bit difficult. So in the beginning, it will not understand that. It will just notice it's like being punished with the lots function because it doesn't produce good sentences. But over time, it will actually learn to do this because you provide, I mean, you also have a ground truth, right? So you have a ground truth answer. And when you compare to the ground truth, the network will learn like, oh, okay, my prediction was not very good. It will not even understand that that was a preposition because it will just output a sequence of integers. It doesn't understand really what that means. It will just understand, oh, that was not good. And over time, things get better. And at some point of time, it will learn to stop automatically at some point. So this is a bit different because here, we have like in the previous solution, the whole generation logic is inside, is part of the network. We generate the outputs as part of the network. Here, it's like we have some logic around the fully connected network that uses the network in a sequential manner. Okay, so implementation-wise, it's really different. This approach here. Okay, now. Okay. I mean, I could using these outputs, I generated myself as optional, but of course, if we already have them, why not use them? It's like a good thing to have. So 2 more remarks on this. So this approach is called autoregressive. Autoregressive because the model takes its own output as inputs again. Okay, it's like this is what it's called an autoregressive model. If I apply my model to its own outputs, sequential. Yeah. So this is also a standard technique in forecasts, time series forecast. Now, what is interesting about this approach is also like I must implement my network so that it can handle sequences, even if the original input was only a scalar. So for example, my original input may be just a number. Number is 17. And the task is generate all sequences up to that number. I generate all numbers up to 17. Yeah. Now, the original input is just a number, and then my network should be only able to treat numbers. But if I use this guy here, then I also need to be able to treat sequences, even if my X is only a scalar. Why? Because I concatenate now the X, like I have 17, but then I say, okay, my first number that I produce is 1. The next number is 2. The next number is 3. So I generate a sequence of of the history, what has happened. And even if the first element, the X was just a number, I'm generating a sequence. And then I need that my network is able to handle sequences, at least in this autoregressive approach. Okay. And I need to make my input layer also bigger, because originally my input layer was only, I needed to be able to process n max inputs. That was the maximum input sentence size. But now if I also need to process my own outputs, well, I need to make the input layer a bit bigger so that I have space for these, for my own predictions here. Okay. Okay. Very good. So this is the autoregressive approach, and then we can see, okay, yeah, interesting. These decoders are much more powerful, or like everything that is a decoder is much more powerful than only a standard neural network that is maybe not working on arbitrarily sized tensors. And we can do it with very simple networks. We will be able to do better with other structures, but what is important for me is that you understand we do not need them necessarily. Even with a standard fully connected network, I can do variable length treatment in input and output. Because as soon as you talk about sequences, everybody says, oh, we need recurrent networks, we need convolutions, transformers, and so on. And in my experience, often the fully connected networks have a very good performance on these tasks as well. But we only need to understand how to reduce them. And, I don't want to say it's always good to use fully connected networks, not at all. But I also don't want us to think that only because I now have variable length, I need to use certain architectures, because fully connected networks couldn't handle that. It's also not the case. Yeah.
In those cases, I'm using padding, the decoder deal with that, or I need to do some pre-processing with the padding before.
Yeah, that's a very good question. So the question is, who's responsible for the padding, the decoder or someone else before? It's a decoder, actually, because the decoder gets a variable length input. So if the decoder is supposed to work with variable size input, he should be able to do the padding. He should do the padding because the input is variable length and not equal length because somebody already did the padding. So this is part of the decoder. The same is for stripping away the paths in the output. So this is part of the decoder. So, but now another interesting question is this. Okay, we now see how we can syntactically do this, but another interesting question is, I mean, what should be the loss function now if we train a network on these variable lengths output sequences? Because for inputs, it's not relevant. Yeah, the loss only refers to the output, and whether the input is variable length or not is not relevant for the loss. But if the output is variable length and is a sequence, then which loss should we use? And actually, there is not one answer to this. I only give one answer here, but actually, you could do research on this question, depending on the task. Okay, so let's now fix a single instance. Okay, so we will not talk about averaging. What we see now will be averaged over the instances, but let's now fix a single one because otherwise the formula becomes really messy. We will say that Yj is Y is the true output sequence. This is what the model should answer as a sequence. And Yj is the true class index at position j. Okay, so it's like the index of the correct word at position j. And Yjk hat is the probability that I assign to word number k at position j. So at the first position, I have a true word. This is y1. This is the word I should predict. At the same position 1, I have a probability distribution or logits, maybe, over all possible words. Okay? And of course, I will predict the words with the highest logit. But I have all these logics for all the words. So these are the two that I have available. In that case, well, I can just use cross entropy position-wise. For each position in the sequence, I can use the cross entropy, which we already know. So cross entropy, we already know, takes the negative logarithm of the correct class, of the probability assigned to the correct class. We've talked about this in machine learning 1, in machine learning 2, in deep learning. Okay, so cross entropy is a known metric. And And here I normalize. This is a normalization not over the instances, but here I go over the position. So for each position in the sequence, I compute the cross entropy at that position. And then I average overall position. So what this means, on average, I have to predict the correct word at each position. Now it is very clear that this is not a very good metric. Why? Let's say I predict the exactly correct sentence, only my first word is different. So I have the correct sentence, but it's shifted by one index. And the first word I predict is an and. So for example, I have to say the dog went out the house. What I do say is, and the dog went out the house. So the sentence is almost perfect, only the first word doesn't match. But since I do a position-wise comparison, he will say you did everything wrong. Okay, so we see this is a really very debatable metric. It's maybe too demanding, maybe, yeah. But it's one possibility I have. And of course, when I do a regression, then I can, for each position, compare what's the true number compared with the number I predict. I can have mean squared error then across the different position in my series. Same argument. Maybe I predict exactly the correct curve. Only in the beginning, I have some mistake that introduces a shift, and then I have a mistake everywhere. Okay, so this is all very debatable. What I want to say here is, if I produce sequential outputs, I also need metrics for sequential outputs. Okay, and one is the position-wise cross entropy loss in the case of classification, position-wise mean squared error, or position-wise squared error for regression, for example. Yeah. And of course, yeah, okay, that's it. So it could be that my mmax is 100, and the true sentence has length 20. The predicted sentence has length 30. Well, then I have 70 symbols where I both say part. There I don't have so I say part with probability 1, and the true answer is part. That I don't have an error on this, but I have an error if I say part. That it means for me the sentence over, while it is not, or the other way around. The sentence is over, so the true sentence says part, but I'm still producing, then I also get punished. That will effectively mean that this guy will learn to stop when it's time to stop. Yeah. Okay. Let's keep it going. So this is decoders. Questions on decoders? I mean, I can give you the choice, actually. So I was wondering, when I prepared the class for today, I was wondering, okay, can we do both in one class? Before I was sure we could, then I thought, okay, could be a bit too fast. We can stop now and talk about encoders only next week. Or we go and we make we cover the encoders as well.
Question is, how work is related to encoders?
Both. So for both, it's important to practice. Yeah. So we need exercise for everything that you talk to. We need exercises because you don't learn here with me. You learn on this fucking sheet. Yeah. And we need exercises for these and these, and they are a bit exhausting. Let's say.
Yeah, we know. But the thing is that maybe it's not about this class. Maybe it's about the time that we need to expend.
Yeah.
In exercise.
I know. So the point is, if we don't make, I don't want to talk about encoders now if we don't have exercises for it. Because then I would say, so what you say is, yeah, we could talk about this, but the homework should only be about decoders. And then I say, no, if the homework is only about decoders, then let's stop here. And we could do this. For me, it would be okay.
If we do both, could we get like the homework like today? And so we have the weekend as well?
Yeah, sure. Actually, I wanted it to be ready already, but I didn't manage to do it. So it took me really like 8 hours to prepare the class, and I also have the homework assignment already advanced, but it's not finished yet. But the objective is to have it ready by tonight, so that you can work during the weekend. The last sheet was available already on Friday.
Yeah, just
And that's always my objective, that the sheet is already here before the class starts, but today I didn't manage to do that. So basically it's your decision. If we don't do it today, then it's one topic less that we can cover in the course. And I wanted to cover the topic. So this is why I said, okay, let's do it. But you decide.
One topic less, but what topic?
Diffusion models. So there's a lot of interesting stuff going on. So let's do a quick poll. Questions binary. Do we continue with encoders now? But that also means that we will have at least one exercise for encoders on the sheet. Or do we stop here? Binary question. So who's in favor of covering encoders now? Right. Who's in favor of stopping here? 2. We continue, but we have the recording, so and maybe I can promise them that the next sheet that will be on autoencoders will be easier. Okay. That would be then a bit the trade-off. Okay. So what are encoders? So let's now suppose that we have, let's make categorical attributes a bit more granular. So a single value for a category attribute will not be just a name anymore, but we can have real objects inside. Okay. So let's say we have a finite set of what we call atomic objects, A for atoms. So one atom could be a city. The possible cities that I have, these could be my atoms. Okay, could be so that would be nodes in a graph, pixels. And then O would be now a structured arrangement over these objects. So I have nodes, and the structured arrangement is that I have connections between them. Which atoms in my molecule are connected? What is the distance between them? Okay. So A is basically a kind of vocabulary. What is it that I can talk about? And O now takes not all, but some of these words, objects, and connects them in some way. That would be a description of a structured arrangement. And O is a set of such objects. Okay. So one element in O could be this here. One element in O could be, these are my cities and they are connected with certain costs and with certain travel restrictions. Okay. Here we are. Now, an encoder is a function that takes such a structured object and produces a tensor valued output. Okay. So again, H here, H is a space of, it's like before, it's a tensor valued space, but it's not a vector space because the dimensionalities are not fixed. Yeah. So everything inside of H is a tensor. Everything here is numeric. Yeah. But it's not like all the objects have the same dimensionality. Okay. So this this space is basically syntactically it's the same like the x and the y in the decode. Okay? So tens are a value, but with arbitrary, possibly arbitrary dimensionality. Okay, so we already talked, like last week, we talked about an embedding, and an embedding was also I map an object to a vector representation. So what's the difference here? The difference is that in reality, in embeddings, as you saw it on the homework sheet, I only put these like atomic objects. Embeddings cannot capture explicit relationships between the objects and the sentence. For example, if I have a sentence, I can have an embedding for each word. But this embedding value does not depend on its row in the sentence. Okay, and I also give you an example now for this. This is one thing, and the other thing is the embedding is always constant, also of fixed size. I do not embed the whole sentence because the sentence is variable length, and an embedding cannot do that. Yeah. So unless, but not, let's not discuss like degenerate cases. So an embedding is not suitable to encode something of arbitrary length. So if I want to encode my traveling salesman problem, for example, well, I cannot use an embedding. So I have a variable length here, possibly, not necessarily, but possibly variable length here and also here. And this is not nothing that an embedding can do. And I don't capture the structural relationships between these objects. Now, importantly, this guy here is finite. So I have only a finite number of objects I can talk about. But O can be infinite. So in the simplest case, O could be sequences. And if I have a fixed number of words, well, I can shape an infinite number of sequences of these words, right? So A is finite, but O not necessarily. And I must be able to encode any arbitrary word or a sentence from O into a tensorial representation. Okay. Now, how could we do this? So one reasonable strategy is to say, I can probably assume that this structured object O, I can describe it through L lists. So I need a number of lists to do this, to describe a single object. Yeah? So the first list is for which words do occur in my structure. For example, so the vocabulary could be everybody, each of us. Okay, so we are 20 people here. Each of us is a atom. And the first list would say, okay, this instance talks about a subgroup. For example, U4. U4 are in the first list. This instance talks about these 4 atoms. Okay, so that would be the first list. And the others are somehow to describe the relationship among the 4 of you. So L is the number of like types of elements we need to describe these objects. So here I have another example for you to maybe, hopefully better understand. Okay. I will already come with the example, but formally that would be this. So an object here, an object is a tuple where I have a list of atoms, like the nodes in my graph, the people about which I talk, the locations of the locations in Colombia, the towns in Colombia could be something like this, okay? And then I have a number of additional descriptors that I can use for this. How are they connected to each other? What is like the average traveling time between 2 pairs of these guys here? What is the risk to travel? Where do I have restrictions and so on? All of these pieces of information, like all these descriptors can be a different like meta column here. And this funny symbol here is called Xi. It's a Greek letter which is called Xi. Okay. So here would be a concrete instance, and this is where the structural component comes in. A single instance would be, well, a list of atomic, like of atoms. Who do I talk about here in this instance specifically? And then here I can encode, like, for example, travel costs. One of these, this is also Xi, but a minor Xi, okay? So this capital Xi, this lowercase Xi. So here I can encode what's the traveling time between this guy and this guy. And the next one, I encode the travel time between A1 and A3, and so on, okay? So importantly, here I have 10 cities, but here I do not have 10 pieces of information of travel times between the cities, because if I have 10 cities, and maybe there are direct connections on streets for, I don't know, 37 pairs of cities, okay? So here I have a list of 10 cities, and here I have a list of 37 descriptions of travel costs, for example. Yeah? And here I have other description of travel restrictions, for example. Okay? So this looks very complicated, right? So I have a single instance is described through a very complicated structure. But if I'm able to handle this well, I can really handle a lot of problems. If I'm able to do this. Like I could solve optimization problems through prediction.
Right, so within the other sets that don't have like atomic objects, those sets are made out of what? Or they can be any?
They can be anything. They can be anything, but we will assume that these can be embedded as well. So let's assume that somehow I can represent these guys through like numbers, integers, okay? So here's an example. I want to represent a graph that is colored. So every node has a color, maybe red, yellow, and blue are the possible colors. What do I need then to do to describe such a graph? Well, first I need to say which nodes do I have. That's the atoms. Yeah? Every node has a name, that's the atoms. Then I need another list that would be Xi1 with the colors. So here, for each node, I must say which color does this node have. Yeah, that would be such a description here. And then I can say, and how are the nodes connected among each other? That would be another Xi. Okay. So that's just one example. This option here, it really gives you an incredible degree of freedom.
Yeah. But the atoms are then implicitly in each of the different like descriptions, right?
The atoms are what?
So, for example, the atoms in the example are nodes.
Yeah.
For the second elements,
the color information.
You will have node and a description of the node.
Yeah, exactly.
And that for all of the different.
Yeah. So here, for example, this Xi1 could be tuples, node name and color.
Yeah.
Yeah. And here you would have tuples of atoms. This atom with this atom.
So the atom is always present in the tuple.
Yeah. Yeah. So these are always used to relate atoms among each other or specify a specific atom in more depth somehow. So here the color just specifies an atom in more depth, gives a certain property. That's the color. Here we're not relating different atoms, but here we're relating different atoms. And you could have even more. You could even say, like, you could also color the edges. And then you say you have a Xi that relates to atoms and a color. Atom 1, atom 2, there is an edge, and the edge has color number 5. So there is really no, in principle, there's no limits of what you can do here with this. So far the objective, because I didn't say yet how we could do this. But our starting point is now that we say all of these elements here are already embedded. That means we are already past the points where we we have complex objects. So if we have a graph, then basically this is precisely our description. How do we describe this graph? Only through elementary events, elementary elements, basic elements that can be described through an embedding. So a graph is a complex object. But if I use this technology here, then I say, okay, but the graph consists of nodes. These are my atoms. These I can embed. This is just categorical attribute. And these are, I can also think like categorical attributes, which I can embed, but together they describe a complex thing. So my point of departure is that all of these elements that I need to describe my object can be embedded and actually have been embedded already. So here in this case, there would be nothing else than saying, okay, my nodes already, maybe the nodes have names, each of us has a name, or the cities have names, but I already projected these names away and I have encoded names, just nodes as integers. Edges are pairs of integers. Who talks to whom? Who has sent a message to whom? Who has wired money to whom? Which node is connected to which one? And colors are also pairs of integers. Yeah. Who, like Max is red, Bob is blue, Alice is green. That's an example. So we're already past the point of having complex things. At this point, we only have, so this technique here basically allows us to reduce the complex object description to a tuple of lists descriptions. Yeah. And maybe one or the other already sees, wow, now it really comes handy that the data loader can give me tuples of arbitrary size. Because now a tuple that is given to from the data loader to me could have in the first position the atom, in the second position this description, the next one this, and then I've a tuple of length L, where I have the description, the tensor value description of my complex object. Yeah. Okay. So what this basically will do, or the objective we will have now is, I mean, we already have embeddings, so what else do we need? If we already have embeddings here, we could basically just put everything into a network and we're good, okay? And somehow this is true, but the task of the encoder will be now to enhance these embeddings, okay? After all, what we want is to get rid of these descriptors. We want to stick probably only the atoms, but we want to represent the atoms not in a general way, but in a specific way that relates to the descriptions here. So if I have a node for John, then I don't want to embed John every time the same way, but the embedding here does it every time the same way. I have an embedding for John, and that is the same vector every time. And what I want to do now is that John gets a different embedding depending on its role in this complex object. Yeah. So what could be the outputs of such an encoder? Where there are different possibilities. So the output space is H, right? That is we said. The only thing that we know is that this guy here must be a set of tensors, space of tensors. So what could be this output space? So let's say we have an input object O, like a graph, for example, and the graph has n atoms. O could be also just a phrase in English, and n would be the number of words. Okay, so O consists of n atoms. What could we output now? So one thing is we could just take this whole thing and put it into a single vector of a fixed size. So it could be that the encoder will say, whatever thing you give to me, I will give you a vector of size 10. That would be a bit what an embedding does, right? Because the embedding always gives me a vector of the same size. I previously was saying I have an embedding size of 10, and then no matter what I put into this embedding layer, I always get a vector of size 10. Well, for an embedding, this is very reasonable because an embedding encodes a categorical attribute. And one can say, well, no matter what the category is, I will always represent it with 10 values. But here, when we get complex objects, maybe it's not so reasonable to say, no matter what my graph looks like that I described to you, I will always describe it through 10 numbers. Describing a graph with 7 nodes in 10 numbers is one thing. Describing a graph with 7 million nodes in 10 numbers may be odd. Okay? So maybe we should have a flexible output here and say we can basically produce sequences of descriptions. So if we have a graph of 10 nodes, we will not output, I don't know, a fixed vector, but for each of the nodes, we will create an embedding. Roughly, this is basically the idea, that we say we have flexible output size for the encoder, and there are several possible cases. First could be that for every atom that goes into the encoder, we also want exactly one output. That would be what I just said. Every input word, every word that goes into the encoder gets a vector representation. So then we would output a matrix. And every word is described through a vector of size 12, for example. All of them have the same. So this would be a bit like the idea we have an embedding, but for each word, not a single embedding for the whole sentence. We have an embedding for every word. But what's the difference here to, I mean, I have already an embedding and I apply it in a for loop for each word. I could do this, but the advantage here is that I can exploit the knowledge. Where is the word in the sentence? Who are the other, which are the other words around? So I have context information, and I don't have context information in a standard embedding. This is what makes the encoder so special here. Could also be that the encoder outputs a sequence, but the sequence length is different. So I input 10 words, a sentence with 10 words, and it outputs a representation for 15 words. Why would that happen? I don't know, but in principle, this could be the case, okay? And it can even be other dimensions, but we should focus to not make things yet more complicated as they already are on this case. So we get an object that talks about n atoms, and now what we want to do is we want to encode these n atoms into an embedding. Each one into an embedding, but what I said before, the special thing is now that the embedding depends on the other objects. It's not like we have the same embedding for John every time that we see John. The embedding for John depends on who else is in the group. Good. So technically, what we then need is an atomic encoder. That means we get an object of n items, and we output. We get an object with n atoms and other context descriptions, who speaks with whom, and so on. But the output will be just a vector, or a list of n items. For every person in the graph, we have one description, H here, okay? And this description is produced by this function G, which is basically the core encoder. This function here takes John, but the difference to the embedding is now it does not only take John, but John and the structure where John is present. So this tells me, please give me the embedding for John in this context, where O is the context. And this here is the difference. In the embedding, I don't have this. In the embedding, I only in the embedding, I can only have a static encoding that does not depend. And I will always produce the same vector for John, or for car, or for apple. It will always be the same encoding. But here, I can have a sentence, and apple stands at some position, is related to other words, and I have this context information here, and that will be part of the encoding. Okay. So this is called an atomic encoder because I will do the encoding of the whole sentence using an encoder of every word. But not only an embedding for every word, because I have this already. I start from there, but I will use this embedding of each word and combine it with the embeddings of everything else I see in this context to get a better embedding of Apple or John. Okay. So what happens here is that before we have this x's, right? And these have gone away now. So here, implicitly, we still have the x's, but the encoder, the output of the encoder does not depend on how many x's we have. It will be just one piece of information for every atom. Okay, so this other information, who speaks with whom, where are the positions, and so on, everything that I have in the x's is gone now. So the encoder takes it and merges it into the representations, but after that, this context information is gone, and we don't have it anymore. So it's not explicit anymore. After the encoder has been used, every information, every complex information I had to describe this object is just part of this vector, of this tensor here, and that's it. Okay, so this is basically the bridge. The encoder is the bridge of, I have the description, the complex description of the object into a tensor. This is what I want, right? Because as soon as I have a tensor, I can use then the neural networks to process this complex object. Okay, let me see this. So figure would be, or the concept would be, I first have the standard embedding layers, or this you already know them. And the embedding layers now produce me for each element in the sequence. So I have 10 words, then, or I have 10 atoms, like 10 people I talk about, and the embedding gives me for each person an embedding, a vector. Tells me, okay, I represent John like this, and Alice I represent like this. And then I have these x's, and the x's also have embeddings. Okay, Bob sends a message to Alice. So these types of information then get here into this. So I have other z values for the x's. Okay, so I have then the complete embedded description of my complex object. And for each, this is why it says embedding layers. It's not just one. For each of these, for my atoms and for the x's, I have different embeddings. So here I have a, and these have different lengths. Observe this, because it could be that, the number of atoms I have is not the same as the elements I have for my first xi and so on. So I have like lists of these tensors, and then these lists go into the encoder, and he will just produce a nice number N1 of tensors, and this is what I really want for my network. Because here the only thing that I have here is that maybe I have a flexible number of tensors, because this length, this number of atoms is flexible, but the rest is well defined. So as soon as I have a decoder that can work with variable length inputs, I can process these outputs here, right? So this is a super powerful concept, this concept of encoders, because it allows me really to represent any type of object in a way that is suitable for processing in neural networks. Even if I only have a fully connected network. We saw today that even with a fully connected network, I can process variable length inputs. Okay, very good. So what we see here is somehow we now get marriage, a pair, okay? So the encoder cannot live without the embedding, because the encoder already assumes tensor inputs. Yeah. So the embeddings have resolved this. It's kind of, we take what we saw last week, and on top of this, we put the encoder. And the encoder will be trained. So inside of this, we also put kind of neural network architecture, right? And when we train this, that he will be trained exactly on the embeddings that we have. That means that when we want to use this encoder in different contexts, we also need to carry on the embedding. These belong together. I cannot use an encoder that was trained on some embeddings now in another context where I have other embeddings, because he wouldn't understand that language. He produces kind of vectorial vocabulary, and he uses this vectorial vocabulary. And it's really important to always use them together. Specific embedding with a specific encoder. Let's see in an example. Here, I want to go here. So if I have an embedding, here I have 2 sentences in English, okay? He went to the bank to open a savings account. This was the sentence we saw before. And he sat by the bank of the river and watched the sunset. So the word bank really has a completely different meaning, because one has to do with money, the other with water, okay? If I have a word embedding like word to vec, this bank will have the same vector as this one. Because it's just, I mean, in the end, every word has a number. Bank could be word number 716. And this word has a specific vector that is associated with it in the embedding. Now, probably it's not good to use the same vector in this context as in this context. And this is exactly what the encoder can now do. The encoder can say, okay, you give me the word embedding. This is the vector for word number 617 here and here. But since the encoder not only has the word, but the whole sentence, the encoder can now say, okay, and what I do with this embedding is I reproject it here. In this context, I project this embedding here. And in this context, I project this embedding here. And then he can use the same word in different ways. So, difference between embedding and encoding is embedding is context free, encoding is context sensitive. Yeah. But the point is, and this is why I introduce it also in this very general way, as we saw, like for this simple example, simple machine translation, it's not so simple, but comparatively simple, because here I don't really have structure. So I can use an encoder to do this here, but it's not necessary. I can also only use the decoder, and he could also be able to learn these different representations for these guys. So why is it still reasonable to use an encoder even for such a problem where I wouldn't need it? Because this is not structural. I don't need an encoder for this, but I can still do it. Well, because it's useful to have not only an embedding for a bank, but an encoding for a bank. Last week we talked about, wow, it's great if you can share embeddings among people. I learned an embedding for words. I can share this with you. This is a great asset if I can share embeddings. But it's even better if I can share encodings. Because for you, it's more useful if you can say, okay, what does bank, which vector should I use for bank in this context? If I just give you an embedding, you don't have it. If I give you just embedding, you can just ask what's the vector of bank, but not, the context doesn't matter. But it's better if I give you, here is my sentence, please give me the vector of each element in the sentence, but the embedding that is context sensitive. And then I will get a vector for bank here from the encoding that is different from the vector I get here. And if I share with you this type of object that can give you these types of embeddings, well, or these types of vectors, this is much more powerful, right? And this is exactly what happened when I think in 2018, when Google released the BERT transformer. Yeah, I think it was 2018. So BERT is a neural network that does nothing else than that. It takes a sentence and gives you for each word in the sentence a vector. Now, why is this revolutionary? Because it's not an embedding, a standard embedding you get, because you get a different vector for the words depending on the context. So if for these two words, if you put this into bird and this into bird, you get two different vectors for bank, which are dependent on what bank means in this context, okay? And that was really revolutionary in the field of deep learning, that there was a public model that you can just download, and it would give you vector representations of words that are context sensitive. Before that, we only had word2vec. And actually, these models are based on word2vec. So it's what I wanted to say here. When I go back for a second. So here I have two papers, which you can look at if you want, where they do exactly this. So before we have embedding only. And if you only have the embedding is in charge of mapping similar things together. This is what you did at home. Vehicles are in the same area and food is in the same area, for example, okay? Now, if we have this stack, first embedding and then the encoder, when they clearly who is in charge of the semantics, the embedding or the encoder? Yeah, the encoder. And actually the embedding is, why do we use the embedding at all? Actually, we only use it to get numbers. There is no semantic left for the embedding. The embedding is only there anymore for mapping a word or so into some first vectorial representation. Okay, but this could even be random. We don't even have to train this. So what they do is to say, okay, we have a two-stack approach. We want to have an encoder, but for an encoder, we need an embedding. So we could have, I think they say it, we could use a random embedding. We have 10,000 words. Every word gets a random vector. And based on these random vectors, then we learn a cool encoding. And you could do this, and they did it. But they said, but if we use as an embedding not random vectors for the words, but we use word2vec, which was already an embedding that somehow organizes things, context-free, but at least it puts them somehow together, then this has much better results with encoding. Okay, so the encoding will use an embedding, and which embedding you use in principle doesn't matter, but in practice, if you use an embedding that already produces a reasonable general purpose representations for the words, that's a good starting point to then create context-specific representations of these words. Okay, so the embedding can help to learn good encodings. So that's the logic here. Okay. Boom. Yeah. I for the next version of this course, I will see again whether I do it this way or not. It's this has been a really dense class.
So go to the previous one.
Yes.
Yeah, because in the last sentence you're saying that embedding is not context aware, but actually they do. I mean, they are calculated based on the words that are close. So that is in some way context aware for that word.
Yeah, but only the training. Okay.
I know, but the sentence says that if they are not context aware at all, so you can
in their usage. So what you say is actually very important, because what we will start then in 2 weeks, I think, is that we will look at the attention mechanism. And what we will see is that actually for the same thing, you need different representations based on what you want to use it for. So the word car should have different embeddings depending on how do I want to use it, for which purpose. Not only on where in the sentence it is, but what do I need this embedding for? Now, what you say is correct. When I train the embedding, then I somehow use the context. But once the embedding is ready, I only have a function that takes as input the word. And now I always get the same number. And what I want, the same the same vector representation for the word, but I would like to have different
No, but my point is that the statement is,
Yeah, the statement is maybe here, one could be a bit more precise and say like, the usage of the embedding does not allow context sensitive generation of the vectors.
So the embedding models that you like can use like ADA and those, they're not really like embedding models, but more encoding models or something like that. This large like text to embeddings model.
Text 2 or word 2? It depends. I mean, text will be encoded. I mean, the problem is a bit that the words embedding and encoding encoders are sometimes a bit mixed up. This whole literature suffers a bit from like overloading like terms. So maybe somebody talks about embedding, but he means encoding in what we discuss now. So that could happen. For example, I mean, typical case is a graph embeddings. So people talk about graph embeddings, but graph embeddings, I mean, that doesn't actually exist even, because by definition, a graph needs an encoding scheme because a graph is a structure. Okay, so, and as you maybe see, I fell into the same trap because last week I also said that embeddings can also encode anything. If I now teach the class again, I would not say that anymore, because I mean, it's not wrong. It depends on what you understand by embedding, but it is also only because now when I prepare this class, I notice well, we need to differentiate this a bit better, because otherwise it becomes really confusing. Now we would say embedding really is what PyTorch does in embedding. It's really just a map from a categorical variable to a vector representation, nothing else. And an encoder maps something like this, but with a context into a vector representation, and does it sequentially, by the way, as well. Okay, but I feel like in the literature this is completely mixed up. Like so, but what is important to understand is I can have context, or I cannot have context. So these are so. Some people say have context-free embeddings and contextual embeddings. So actually, I would say BERT, like this Google model, is an encoder, and actually that's also the name. Yeah? So it's a bidirectional encoder, bidirectional encoder. But there are people who call BERT a contextual embedding. Then you see that like, things go all over the map. So, summary. So today we saw encoders and decoders. They have nothing to do with each other. It's just completely different things. Okay. So a decoder, basically, what does it take as an input? Well, any type of tensors, and it can output anything. So here can be a scalar or a sequence. Here can be a scalar or a sequence. Yeah. So do I have variable length input? So, could be. Could not be, and here as well. Okay, so the task is just convert something into something else, and the something input could be a scalar or a sequence, and the output could be also a scalar or a sequence. The only thing is that everything must be tensorial. This is the only thing, and the encoder takes a structured object that has piecewise been embedded and outputs a sequence of tensors. Now, why do we have a yes here always? Because if this structured object would not be variable length, well, then it wouldn't be structured in the first place. Okay, so here it's somehow by construction or by definition of this whole thing that this thing here must be somehow variable length. We must be. I mean, if we only can treat structures that always have the same size, then somehow it's not really structural, okay? So the graphs, the sentences, all of that goes into this must be somehow, we must allow for variable length here, otherwise it doesn't make sense to talk about these contextual objects, okay? Okay, And of course, I can put them together, but I can have systems that are only encoder, no decoding. BERT is such a system. Only encoding, there's no decoder. I can have systems that are only decoder, no encoder. GPT is a decoder without encoder. ChatGPT is only decoder, no encoding. Yeah. This is why it's so confusing. And I don't want anybody to think like, we have a process where we compress, therefore we need an encoder, then we decompress, therefore we have a decoder, because it's not that way anymore. I can have none of them, I can have one of them, I can both of them. Okay. And so finally, decoders are tensor-based supervising learning models, any neural network that we can build basically, that are based only on tensors. Yeah? And encoders produce context-aware embeddings, if you want to use the term here, context-aware embeddings, specifically, and this is specifically useful, not even for textual, we can use it for text, but it's specifically useful for complex objects. Okay. Molecules, argumentation graphs, maybe causal networks. So you can do a whole lot with all these things. So yeah, now it's time to practice, I guess. So
Another question. I have been embedding, and how do I represent the relation with embedding? That's one part I can understand. You said that an atom has the embedding and the context, but how the context is represented?
Also through embeddings. So here I have an example for this. So here. So if you have a map of Colombia, then every city or every town could be embedded with a number. Okay, so that would be embedding for the objects here. So think of these like these are sets of categories. Here I have the cities. Here I have the descriptions of how cities are being connected. Here I have so the description here is Bogota connected with Medellin? No, at least not like directly. If we think of a map where we have like nodes like our crossings. Is Bogota connected with Chia? Yes, because there is an immediate way without passing anything else. Okay, so you can say Bogota is 7, Chia is 9. And then you have the tuple 7, 9 here in the description of this structure. And 7 and 9 have embeddings as well. So the integer 7 goes, the 7 goes into a vector description. The 9, like Bogota, goes into a vector description. Chia goes into a vector description. And these two together are then part here.
Okay, and from that vector, from that representation, also goes to the embedding. I mean, so everything's in embedding.
Yeah, everything here. That's why I say everything here is already embedded. Okay. But the point is, why can't I have just a single tensor? Because all of these guys have different lengths. I have 7 cities, but I do not have 7 streets. Yeah. So there is no way to put these together efficiently into a single tensor. But doing this, so in the end, I want to put my 7 cities context dependent into vectorial representations, and I want to use these embeddings for this task.
And another question from that point of view, if I remember that we have to provide negative samplings, so this is not required here.
No. Okay. Well, that depends on how you want to train your encoder. So BERT, this encoder, is also trained in which words co-occur in different sentences. So you can also do this to train an embedding. Let's see whether I put something like this on the homework sheet, but if I do, I will explain to you exactly how you can do this. Very good question.
Thank you.
Another exercise. The next one's in 25 minutes. So, yeah. Okay, good. Then, yeah, good luck with the. Yeah, but as I said, then next week we will go a bit more slowly. Actually, next week then we will only do like 1 hour class, probably because today we use too much time. And try to relax a little. It's.